All right, so this is section 3.4, pre-calculus 30. This is question number 4D. And this is a good question to, you have to know how to do this question. We're looking at the graph and we're identifying some very important things like intercepts, intervals where the graph is positive or negative, and explain whether the graph might represent a polynomial that has zeros of multiplicity 1, 2, or 3. So we're looking at the zero behavior as well for part 3. So, you guys can see that? All right, so state the X intercepts. Okay, now we may have to zoom in a little bit here. Maybe I'll make this just a bit bigger so you guys can see that at the back. But the X intercepts obviously are where the graph touches or crosses the x-axis. And so I'm identifying an x-intercept here. Now this is a y-intercept down here. Okay, that's y. Here's another x-intercept. So it looks like the graph only touches the x-axis twice. Okay. So state the x-intercepts. Well, we have negative 1, 0. That's the point for one intercept. And then we have 3, 0 is the second intercept that I can identify there. Okay, we're all good with that first part? Okay, number 2, state the intervals where the function is positive or the intervals where it's negative. So remember, this is the positive up here for y. And we're talking about the positive values for y. The negative values would be down here. These are the negative values for y. So it's above the x-axis and below. See all the negatives here, right? So wherever this graph is actually in this area right here, that's where the graph is negative. And wherever the graph is above the x-axis, that's where the graph is positive. And how we identify where that graph is negative and positive is by stating the parts of the domain. That is, state the x values that are attached with that part of the graph. So for number 2 here, the intervals. Now intervals, remember, are like sections of the x values, of the x-axis, if you want to think of it that way. Okay, positive. Okay, so positive. So we've got f of x, okay, is greater than 0, okay, on the intervals of. Now let's just try and figure this out. So it's above the x-axis, really only in one spot here, and it's this part right here. This goes forever up and forever left. So it just keeps creeping over left as well. So the x that we're identifying here is less than negative 1. Everything that's on this side of this intercept. So interval, you guys don't know interval notation, I don't think yet. Forget it, that's calculus. So we've got x less than negative 1, okay? Now we're not going to do or equal to, technically, because 0 is not negative or positive. So we're going to say just less than negative 1, not less than or equal to, okay? All right, what about where f of x is less than 0? That's where the function is negative. So we look down here. Well, the graph seems to be negative on a lot of spaces here. Now, here's one little catch, okay? You could think of this as, hey, everything, all x values that are greater than negative 1, because the graph is below the x-axis the whole time. Well, technically it's actually not. This might seem a little bit picky, but do you see where x equals 3 here? That's 0. See, the graph is actually 0 there. That's an intercept. So you can't state that as part of your interval. So we have to go here. X is, or f of x is negative on, and you can say where x is, now we're going to have to say between two values. So let's say from negative 1 less than x less than 3, okay? And you could put these inside braces. That's a good idea, because we're talking about a domain. So you see it's between here and here, not including this point and not including this point. That's the first section. And then also, you can state the rest of it. So now everything greater than positive 3. So x is also greater than 3. All right? That's where it's positive. I'm sorry, negative. So the graph is below the x-axis here for this section, and then it's actually 0 there, so we can't count that point. But then here, it's everything greater than 3 as well. Now, explain whether the graph might represent a polynomial that has zeros of multiplicity 1, 2, or 3. That's easy. We look at the zero behavior, and I'm going to erase a bunch of this stuff so we can look at the graphs right around the x-axis, right around the intercepts. And this is tangent to and crosses. Do you see that? I'll zoom in. Okay. This is tangent to and crosses. That's not a straight cross. It kind of bends down like that. It kind of curls up to the graph and then curls away. So this would be a multiplicity of at least 3. Okay, not 1, because 1 is a straight cross. 3 would be tangent to and cross, and then all the other odd ones greater than that, like 5, 7, 9, would be the same thing. So we could say that probably at this 0 it has a multiplicity of 3. This one here is tangent to but does not cross. So that is a multiplicity of 2, or any exponent that's even, right? And because this graph here, if it was an exponent 4 or 6 or 8 or 10 or 22, you would have the graph looking like quite a flat bottom graph like this. It would look something like this. That's what happens when the exponent is even but greater than 2. It starts to flatten out at that point. Instead of being a nice rounded parabola shape, it kind of has a flat bottom like that. So we could probably say, you know what, there's a multiplicity of 3 here, and a multiplicity of 2 there, and you just state that for 3. So we might just explain this way. Multiplicity of 3 at x equals -1, which we identified, and multiplicity of 2 at x equals 3. That's a fine way to answer that part of the question. Okay, does that help? 4D? You asked about 4D? Does that help? Okay. Any other questions about this one? All right.